Here's my explanation and example problem for constant pressure calorimetry. So I chose problem 51 from chapter 6 in the chem textbook, and I synthesized the important information here. We have 50 milliliters of a 0.1 molarity AgNO3 as part of our solution. We are also given that 50 milliliters of 0.1 molarity HCl is also used. And these two come together to create Ag plus aqueous plus Cl minus aqueous, which will yield AgCl in the solid form. We are also told that for the solution, the initial temperature is 22.6 degrees Celsius and the final temperature is 23.4 degrees Celsius. We are also told that the combined mass of the solution is 100.0 grams and the specific heat capacity is 4.18 joules per degrees Celsius times grams. We also know that from this information, and seeing as we're trying to find the constant pressure calorimetry, we need to use the equation E equals mc delta T. E being the heat, which we are trying to find in this problem. We're trying to find the heat of the solution. So the heat is equal to the mass in grams times the specific heat capacity times the change in temperature. So we are given all this information. The E is equal to 100 grams because the combined mass of the solution is 100 grams times the specific heat capacity of 4.18 joules per degrees Kelvin times grams, and then times the change in temperature. So the final minus initial, final being 23.4 minus initial 22.6, which will be 0.8 degrees and change. And then you plug this in your calculator and you will get 334.4 joules released in heat, or you can write this as negative 334.4 joules because the reaction is exothermic, and we can see that because the final temperature has increased from the initial, meaning that it's releasing heat and thus exothermic. So from that, what we can do is we see that the problem asks us actually to find the heat in kilojoules per mole of AgCl. And we have just found the joules, so now we need to find kilojoules. And we do that by doing the kilojoules to joule ratio, which is 1 kilojoule in every 1,000 joules. So now we are in kilojoules, but now we also need to have this over moles of AgCl. To find moles of AgCl, it's a simple limiting reactant stoichiometry problem with the 50 milliliters of 0.1 molarity AgNO3 and 50 milliliters of 0.1 molarity HCl coming together, and from that we can find the moles of it, which would be 0.005 moles of each kind, meaning that you can use either one as the limiting reactant in this case. So, and then from there we see the mole-to-mole ratio, which is just 1:1. So in the end, it's 0.005 moles of AgCl being produced. And then from there, we multiply this all together and you get negative 66.88 kilojoules per mole as our answer. And then also part of this topic is coffee cup calorimetry. So I have here a diagram for it, and a coffee cup calorimeter is consisting of two nested styrofoam cups, so one inside the other, an insulated stopper to keep the heat in, a stirrer to ensure that the solution is completely aqueous, so in other words, the solid that you put in no longer is a solid and rather has dissolved, and then a thermometer so you can find the change in temperature. And so a coffee cup calorimetry usually involves water, and by carrying out a reaction in aqueous solution in a simple calorimeter such as this one right here, one can indirectly measure heat change for the system by measuring the heat change for the water in the calorimeter, meaning that instead of actually finding the heat change for the solution, we're finding the heat change of the water, which in theory will be equal to the heat change of the solution. This has been my explanation and diagram for constant pressure calorimetry. Thank you.
In another experiment, liquid heptane is completely combusted to produce CO2 and H2O as represented by the following equation. The heat of combustion for 1 mole is negative 4.85 times 10 to the third kilojoules. Using the information in the table below, calculate the value of delta H for C7H16 in kilojoules per mole. What's given in the table below is the delta H values for CO2 and H2O. To solve for this, you use the equation delta H is equal to the sum of delta H products minus the sum of the reactants, and it is 7 times CO2 because there is a coefficient of 7 in the balanced equation, plus 8 times H2O minus the unknown of C7H16 plus 11 times O2. So since you are given the heat of combustion negative 4.85 times 10 to the third, you set that for delta H, and you equal that to 7 times negative 393.5 plus 8 times negative 285.8 minus the unknown C7H16 plus 11 times 0, and it's times 0 because O2 is by itself. So then you get negative 4,850 is equal to negative 2,754 minus 2,286 minus delta H of C7H16, and you get delta H for C7H16 is negative 191 kilojoules per mole. For number 2, a 0.0108 mole sample of C7H16 is combusted in a bomb calorimeter. You have to calculate the amount of heat released to the calorimeter, and so for this you solve it by doing the heat released is equal to 0.0108 moles of C7H16 divided by 1 mole of C7H16 times negative 4,850 kilojoules, which is equal to 52.4 kilojoules released. For part 2, you are given the total heat capacity of the calorimeter, which is 9.273 kilojoules degrees Celsius. Calculate the temperature change of the calorimeter. To solve for this, use the equation Q equals C delta T. Q is 52.4 for what you just solved for, and that's equal to C delta T, and C is given to you, which is 9.273 times the unknown of delta T. Therefore, you do delta T equals 52.4 divided by 9.273, which is 5.65 degrees Celsius. But since it is degree Celsius negative 1, you have to do negative 52.4 divided by 9.273, which is equal to 5.65 degrees Celsius.
Okay, so here is an example problem for calculating delta H in thermochemistry. Delta H equals standard enthalpy of formation, and this means that the standard enthalpy of formation of a compound is defined as the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all the substances in standard states. So this basically means that it's the sum of products minus the sum of the reactants, their delta H values. And the standard state of an element exists under conditions of 1 atm and 25 degrees Celsius. So that's what the degree sign means. That means standard conditions. So here's an example problem. 2H2 plus O2 yields 2H2O. And like I said earlier, the equation is delta H, or standard enthalpy of formation, equals the sum of the products minus the sum of the reactants, the delta H values for all those. And so in this case, delta H is going to be equal to 2 times negative 286 kilojoules per mole. And you can find the delta H values in the back of the textbook in a chart. And the delta H value for H2O is negative 286, but we multiply that times 2 since there are 2 moles, the coefficient in the reaction. And then you subtract that by the delta H values for the reactants, but they're both in their elemental states, which means that their delta H values are 0. And since the delta H values are 0, that will cancel out the times 2 for the H2 and plus O2 because it's the sum of all the reactants. And that'll leave you with a delta H value of negative 572 kilojoules per mole.
Here is an example of how to do a Hess's law problem. Calculate delta H for the reaction C2H4 plus H2 yields to C2H6, given the following data on the screen. A helpful thing to note when solving is to compare the elements in the reaction you're solving for and the individual reactions to see what elements you need to keep and which elements you need to cancel out. In this reaction, we can note that we need to keep C2H4, C2H6, and H2. To get the elements on the right side of the equation and cancel out other elements, we need to try to flip and multiply reactions. In order to get this 2 moles of C2H6 to the product side, we need to flip the second equation. What we do to the equation, we must do the same to its delta H. And therefore, we must multiply the equation's delta H by -1 to flip the sign. In order for the elements that we need to cancel out to have the same amount of moles on each side, we need to multiply the first reaction and its delta H by 2. The coefficients of the first reaction is now doubled and its delta H becomes negative 2,822 kilojoules. Because we flipped the second equation, the reactants are now the products, while the products are now the reactants. This makes the second reactant's delta H now a positive value rather than a negative. For the third reaction, it remains the same because we did nothing to it. Now that these changes have been made to the reactions, we can cancel out the 7 O2s, the 4 CO2s, and the 6 H2Os on both sides. To find the delta H value for 2C2H4 plus 2H2 yields a 2C2H6, we sum the energy changes of the individual reactions comprising it, which gives us a delta H value of negative 1,547.5 kilojoules. However, the equation does not exactly match the original reaction given to us. In order for the coefficients to match, we need to divide the reaction and its delta H by 2, and this gives us a delta H of negative 773.75 kilojoules, which is our answer.